There is a phrase that almost everyone has heard at least once, usually spoken with great confidence at dinner tables, in philosophy classrooms, or during late-night conversations where someone wants to sound profound. The phrase is simple. Everything is relative. People invoke it when defending personal taste, when avoiding moral arguments, when explaining why one culture cannot judge another, or simply when trying to suggest that truth itself is a slippery, subjective thing that bends according to whoever is doing the looking. And somewhere in the background of all these conversations, the name of Albert Einstein floats like a silent endorsement, as though the greatest physicist of the 20th century spent his life proving that nothing is fixed, nothing is certain, and every perspective is equally valid. The problem is that Einstein never said anything of the sort. In fact, what he actually discovered was nearly the opposite. The theories that bear his name, the special theory of relativity published in 1905, and the general theory of relativity completed in 1915, were not attempts to dissolve certainty into a fog of subjective interpretation. They were precise, mathematical, and deeply counterintuitive descriptions of how the physical universe actually behaves, built on a foundation that was, at its core, about finding what does not change, what remains absolute, what every observer in every corner of the cosmos would agree upon. Einstein was not a philosopher of relativism. He was a hunter of absolutes hiding beneath the surface of appearances. To understand why this matters and why the confusion runs so deep, now it helps to begin not with Einstein himself, but with the world he inherited. By the late 19th century, physics had reached a peculiar crossroads. On one side stood the towering achievement of Isaac Newton, whose laws of motion and universal gravitation had described the physical world with extraordinary precision for over 200 years. Newtonian mechanics rested on intuitive foundations. Space was a fixed, absolute stage, existing independently of anything inside it, and time was a universal river flowing at the same rate for every observer everywhere. These were not assumptions that needed defending. They were simply obvious. Everyone agreed that a second was a second, that a meter was a meter, and that two events either happened simultaneously or they did not, regardless of who was watching. Yet on the other side of that crossroad stood James Clerk Maxwell and his equations describing electromagnetism. Maxwell had shown with breathtaking elegance that electric and magnetic fields propagate through space as waves, and that these waves travel at a fixed speed, approximately 300,000 kilometers per second. This was the speed of light, and it was written directly into Maxwell's equations as a constant. The problem, the one that would eventually consume a young Swiss patent clerk named Albert Einstein, was that Maxwell's equations did not say anything about the speed of light relative to a particular observer. They seemed to suggest that light traveled at that fixed speed, relative to nothing in particular, or perhaps relative to some mysterious medium that filled all of space. A substance physicists called the luminiferous ether. The ether was a reasonable hypothesis. Sound waves, after all, travel through air. Ocean waves travel through water. It made intuitive sense that light waves would need something to travel through as well. And if light moved through the ether at a fixed speed, then observers moving relative to the ether should measure different speeds for light, just as a swimmer moving against a current feels more resistance than one moving with it. In 1887, Albert Michelson and Edward Morley designed an experiment of extraordinary precision to detect this effect, to measure the difference in the speed of light depending on the direction the Earth was moving through the ether. The result was one of the most famous null results in the history of science. There was no difference. No matter how the apparatus was oriented, no matter what time of year the measurement was taken, the speed of light was always the same. This was not a minor inconvenience. It was a catastrophe for existing physics, a result so strange that the scientific community spent nearly 2 decades arguing about how to explain it away. Various proposals were offered. Perhaps moving objects contracted slightly in the direction of motion, compensating for the expected difference. Perhaps clocks slowed down as they moved. These ideas, developed by Hendrik Lorentz and George Fitzgerald, captured something mathematically correct about what was happening, but they offered no satisfying physical explanation. They were patches applied to a framework that was quietly breaking apart. Einstein's genius was not to solve the problem within the existing framework. It was to step back entirely, look at the foundations, and ask what assumptions everyone had been taking for granted without examination. In 1905, working in the patent office in Bern, without access to the great laboratories of Europe, and without close collaboration with the leading physicists of the day, he published a paper titled On the Electrodynamics of Moving Bodies, and in it he laid out what would become the special theory of relativity. The paper began not with equations, but with principles, with two simple postulates that would change everything. The first postulate was that the laws of physics are the same for all observers moving at constant velocity relative to one another. This idea, known as the principle of relativity, was not entirely new. Galileo had understood something similar centuries earlier. A person below the deck of a smoothly sailing ship cannot tell by any mechanical experiment whether the ship is moving or standing still. Einstein extended this to all of physics, including electromagnetism. There is no experiment, mechanical or electromagnetic, that can determine absolute rest or absolute uniform motion. There is no privileged frame of reference from which the universe looks the way it truly is. Every observer moving at constant velocity has an equally valid claim to being at rest. The second postulate was the revolutionary one, the one that shattered the Newtonian picture of space and time. Einstein simply declared that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. A person standing still and a person moving at half the speed of light will both measure the same beam of light traveling at exactly the same speed. This was not a wild speculation. It was what Maxwell's equations implied and what Michelson and Morley had measured. But Einstein was the first to take it seriously as a fundamental fact about the universe, rather than a problem to be explained away. The consequences of these two postulates, when followed with strict logical discipline, are extraordinary. If the speed of light must be the same for all observers, then space and time themselves cannot be fixed, universal, and absolute. Two observers moving relative to each other will disagree about the lengths of objects, about the rates at which clocks tick, and crucially, about whether two events that appear simultaneous to one observer also appear simultaneous to the other. These are not illusions or measurement errors. They are genuine features of reality as described by the geometry of spacetime. A clock on a fast-moving spaceship really does tick more slowly than a clock on Earth. A ruler moving at high speed is genuinely shorter along its direction of motion than the same ruler at rest. These effects, time dilation and length contraction, have been measured with extreme precision and are not matters of opinion or perspective. But here is the crucial point that the dinner table philosopher so often misses. What Einstein's special relativity actually established was not that everything is relative, but that something is absolute that had never been recognized as such before. While different observers disagree about time intervals and spatial distances, they all agree on a specific combination of space and time called the space-time interval. While they disagree about simultaneity, they all agree on whether one event could have caused another, on the causal structure of the universe. And most famously, while speeds are relative, the speed of light is not. The speed of light is the one constant that every observer in the universe shares, the bedrock of invariance on which the entire theory rests. The equation that most people associate with Einstein, E equals mc squared, emerged from special relativity and carries a similarly absolute character. It states that mass and energy are equivalent, that a certain amount of mass contains a specific quantity of energy, and that the conversion factor is the speed of light squared. This is not a statement that energy is whatever you decide it is or that mass is in the eye of the beholder. It is a precise, fixed, universal relationship that holds everywhere in the cosmos, tested in particle accelerators and nuclear reactions, and the cores of stars. For 10 years after publishing Special Relativity, Einstein wrestled with a limitation of his own theory. It described the physics of observers moving at constant velocity, but it had nothing to say about gravity, and it could not account for accelerating motion in any deep way. Gravity, as Newton had described it, was an instantaneous force acting across empty space, and this picture was fundamentally incompatible with the structure of special relativity, where nothing, including the influence of forces, can travel faster than light. Einstein needed a new theory of gravity, one that would be consistent with everything special relativity had established. The path to general relativity began with what Einstein later called the happiest thought of his life. He imagined a person falling freely under the influence of gravity, a person jumping from a rooftop or floating in a freely falling elevator. That person, in the instant of free fall, feels no weight. The effects of gravity vanish. If the person releases a ball, it does not fall away from them, but floats alongside them, as though gravity had simply ceased to exist. Einstein recognized that free fall and weightlessness in empty space are physically indistinguishable from each other. A person in a sealed box cannot tell from the inside whether the box is floating far from any gravitational source or whether it is falling freely toward a massive planet. This equivalence between gravitational and inertial effects became the foundation of the entire general theory. What Einstein eventually showed, through years of difficult mathematics that pushed him to the limits of his knowledge and forced him to collaborate with mathematicians who understood geometries he was still learning, was that gravity is not a force at all in the traditional sense. It is a curvature in the fabric of space-time itself, caused by the presence of mass and energy. Objects moving under the influence of gravity are not being pushed or pulled by any external force. They are following the straightest possible paths through a curved space-time, what mathematicians call geodesics, and the Earth orbits the Sun, not because there is a mysterious rope of gravitational attraction pulling it inward, but because the Sun has curved the space-time around it, and the Earth is simply following the natural contour of that curved geometry. The equations Einstein arrived at, the field equations of general relativity, describe precisely how the distribution of mass and energy curves spacetime, and how that curvature in turn determines the motion of matter and energy. They are among the most beautiful and most demanding equations in all of science, 10-coupled nonlinear partial differential equations that reduce to Newton's law of gravity in the weak field limit, but diverge dramatically from Newtonian predictions in extreme conditions. They predict phenomena that Newton never imagined: the bending of light around massive objects, the slowing of time in strong gravitational fields, the existence of black holes where space-time curves so severely that nothing can escape, and the expansion of the universe itself, a solution that so disturbed Einstein that he initially introduced an extra term into his equations to prevent it, a move he later described as the greatest blunder of his life. Every prediction of general relativity that has been tested has been confirmed. Arthur Eddington's 1919 solar eclipse expedition measured the deflection of starlight by the sun and found it matched Einstein's prediction exactly, in the process making Einstein famous around the world. Atomic clocks on satellites run at measurable different rates than clocks on the ground, due to both the velocity of the satellite and the difference in gravitational strength. And the GPS system that guides cars and aircraft must correct for both effects constantly, or it would accumulate errors of kilometers within a day. Gravitational waves, ripples in spacetime itself, produced by catastrophic events like the merger of black holes, were detected for the first time in 2015. A century after Einstein predicted them, by instruments sensitive enough to detect a distortion smaller than 1,000th of the diameter of a proton. General relativity is, in every testable respect, one of the most precisely verified theories in the history of science. And like special relativity, it is built not on the dissolution of certainty, but on the identification of deeper invariances. The spacetime interval of special relativity becomes, in general relativity, the metric tensor, a mathematical object that encodes the geometry of curved spacetime in a way that is independent of the coordinate system any particular observer chooses. Different observers using different coordinate systems will write the metric in different ways, but the physical reality it describes, the curvature, the distances, the causal relationships, is the same for all of them. The theory is covariant, meaning its equations take the same form for all observers regardless of their state of motion. But this covariance is precisely the opposite of the claim that physical reality depends on who is looking. It means that the physical content of the theory is independent of any observer's arbitrary choices. The confusion between Einstein's relativity and philosophical relativism almost certainly has something to do with the word itself, perhaps also with the unsettling nature of what relativity does say. It is genuinely strange that two observers can disagree about the time between two events or the distance between 2 points. It is genuinely disturbing that simultaneity is not universal. These features of relativity do challenge a certain naive picture of reality, the idea that there is one universal clock and one universal ruler against which all measurements are made. But they replace that naive picture not with chaos and subjectivity, but with a more sophisticated and more beautiful kind of order, one in which the relationships between space-time events, the causal structure of the universe, the speed of light, and the equations of physics are shared by every observer everywhere. Einstein himself was aware of the misappropriation of his work and found it troubling. He reportedly preferred the name invariant in theory, the theory of invariance, to the name relativity, precisely because the word relativity invited the misunderstanding that has persisted for over a century. What he had discovered was not a license for every person to construct their own reality. It was a deeper description of a reality that is shared, objective, and governed by laws that hold everywhere and for everyone. The distance between that vision and the casual philosophy of everything is relative is enormous, and it matters. It matters because science depends on the idea that there are facts about the universe that are true regardless of who is looking, and that careful observation and rigorous reasoning can bring us closer to understanding them. It matters because Einstein spent a decade of relentless, disciplined intellectual work to build general relativity. And that work was not an exercise in showing that physics depends on perspective, but an exercise in finding the deepest, most observer-independent description of gravity that was mathematically possible. And it matters because the confusion, so widespread and so persistent, does a disservice not only to Einstein but to the very idea that human thought at its best can cut through the fog of appearances and discover something true about the nature of the world. What Einstein really said was something far harder and far more beautiful than everything is relative. He said that the universe has a structure, that the structure is geometric, that it bends and curves in response to mass and energy, that time and space are not separate and absolute but woven together into a single fabric, and that the equations describing this fabric are the same for every observer in the cosmos. He said that beneath the surface of apparently different measurements lies a deeper layer of invariance, a shared reality that transcends the perspective of any single observer. He said, in the language of mathematics, that the universe is not a collection of opinions. It is a cosmos, and it has laws.